we have a free bandwidth, okay? The bandwidth of the signal that look like this one, okay? The bandwidth Bm, okay, of Bm, okay, of the electrical filter, okay? Bs is contained in Bm. The electrical filter provided by a notch function, you see here is a notch function around the zero in order to remove the DC component, because the people is not interested to the DC component, okay, never, okay. So this is the blue filter with a bandwidth Bm. Bs is the bandwidth of the signal itself, and the BO, this is not a zero but is an O optical. B optical is the yellow bandwidth, okay? You see that the yellow bandwidth is supposed to be more larger than the electrical bandwidth, and this is correct because usually if you consider an optical filter, okay, like a filter of WDM signal, the bandwidth should be of the order of 100 G or 50 G, depending on the grid, no? So 100 G is much more larger than 10 G. So it's 10 times more larger. So you may suppose that in this domain, electrical domain, this is quite flat. So we, at the moment, we don't care about the Q of this filter, okay? Because if we care about the Q, it's very complicated from the mathematical representation, okay? Because we have to design the exact transfer function of the filter, okay? So we don't care, okay? Because so we suppose that in first approximation is Bm, Bs, Bo, okay? This is our receiver. You see that they never change. But now we already know all the noise terms affecting the receiver. This, I emphasize that this square here is just one of the many colored channels that arrive here. That is, in other terms, here we arrive to the photodetector by one of the possible channels in my demux, WDM demux. Okay, and then I have here another channel, here another channel, here another channel, and so on. So the full collection of the channel look like this. And I remind you that this is organized following the ITUT grid, okay? And this is organized from 191 terahertz 50 gigahertz, 191 terahertz 100 G, 191 terahertz 150 G, so on, so on, so on. So this is terahertz, the scale. Okay, but now the scale is also the electrical scale. So there are a mixing here in the scale, in the horizontal coordinate. You have a mixing of frequency, electrical frequency, when we talk about electrical filter, and optical frequency, okay? You see this graph? Anybody understand this? Understood this? Now, the PS, okay, BO is usually bilateral bandwidth, which corresponds both to the positive and negative frequency in the electrical domain, because you see here, of course, it's better, you see here that naturally BO is bilateral, no? Because this is the spectrum, optical spectrum, so BO is naturally bilateral. And even the signal you may consider bilateral signal, no? Because you have the negative frequency in terms of electrical, or usually frequency in terms of optical. So in optical there are no negative frequency, there are simply a lower frequency, okay? But in electrical we talk about negative and positive frequency, but not in optical, okay? Okay, now we assume that the integration time is simply 1 over 2 Bm. Why? Because okay, in first approximation this is correct. Okay, then there are some coefficients which depend on the specific transfer function of the filter. Okay, so this could be 1, 2, pi over 2, depend on the filter, no, and how many harmonics you consider, no, because typically the filter look like this, so it depends if you end to the first harmonic here, 2, 3, 4 factor. But we assume to simplify this situation. Okay, now finally we arrive to the signal to noise ratio, because now we have signal to noise ratio in electrical is S average squared divide variance. Or in other terms, if I consider the count rate, the variance of the count rate time E squared, and here E squared time the average of the count rate. Okay. And now we assume that we don't know if here there was or not an amplifier. So we assume in general that here the light that arrives against the photodiode, this is the photodiode, is a mixed light, okay? Mixed light. So it's neither a pure laser light nor a noise light. It is a mixture of this one. So we already know from Laguerre what is this variance, because the variance is exactly this one, okay? So now let's already call T capital 1 of dBm integration time. Let's assume now that the optical noise present a bandwidth much more larger than the signal bandwidth, and that will be detected through the optical bandwidth below. That is, all the noise component enter with a bandwidth larger than the electrical bandwidth and cross the optical filter. Then let us assume that the detection that arrive here, okay, in the photodiode is monomode. So we don't consider the different beta, okay, because otherwise we open a chapter complex. Okay, we just consider monomode transmission, remove the problem of the beta. And we also don't consider the problem of the polarization in this moment. So we don't care about the polarization of the light. So light arrive is monomode, don't care about the polarization, okay? The number of statistically independent modes, these are temporal modes, that is the mode of the statistic of the measurement, so it's nothing to do with the mode of the propagation, okay, this is a mode of the sampling, okay, is BO divided to BM, you agree? Because as first approximation, the number of statistical modes is this one, you remind last week, okay? So we make this free assumption, okay? So that is okay. We arrive here, and then we make this free assumption. And then what we think? We have to evaluate the different term, no? That is, we already evaluated different term because MS is alpha PS, okay? Where alpha is the coefficient connected with the responsivity. That is, alpha is eta Hν, where eta is the photo counting efficiency, that is the quantum efficiency, and Hν is the energy of the photon, okay? So MS is alpha PS. So this one is alpha PS A squared, okay? And if, okay, and then I suppose to make an integration, okay, for the time t. In order to obtain this, I made an integration for the time t. That means that I consider alpha PS integrated from dt from 0 to t, and this gives me my mt. Okay? So this one is the numerator. Okay? I repeat. I evaluated this term and then this term. Okay? Don't care about e squared, because you see that you may simplify e squared. Okay? So you may remove e squared. So you have alpha ps t capital. Then, what about the denominator? In the denominator, I have again alpha ps integrated on t. Again, the noise, these are the short noise term or corpuscular term of the variance that we already see, and these are the beating term. Okay, so I have alpha pst, alpha pnt, where pn is the power of the noise, and then I have alpha pnt squared divide m, because it's the beating of the noise with itself. And then I have 2 mu s mu m divide m. Okay, but since m is by definition, this is my optical bandwidth, this is my 2bm signal. Since m capital is bo divided 2bm, okay, what we obtain, instead of m, I put bo divided 2bm, so you see that since m is the denominator, bo is here, the inverse of m 2bm, bo 2bm, okay? And then let me divide by t squared the numerator, you see numerator, I divide by t squared the numerator and the denominator. So this is alpha ps 1 over t, alpha pn 1 over t. This is a t squared, so I cross this. And this is a t squared, I cross this. So I obtain this. Anybody follow? Very simple algebra, okay? Just algebraic manipulation, no more. Okay? Then, let's introduce the noise average power spectral. What is the noise average power spectral? Is by definition, my spectral level is Pn divide this bandwidth that I suppose a constant, that is Bo. Okay? Okay? So, I call this NO, N optical. So instead of having this BO divided Pn here, I have NO. Okay, you see here, this term here give NO. Then instead of having 1 over t here, I have 2bm in the numerator. So I collect all the 2bm, okay? And here I have NO, here I have NO. So with this position, it's just an algebraical change, I obtain this expression. Okay? E alpha ps squared divide E squared alpha ps 2bm, alpha pn 2bm, alpha squared pno 2bm, 2 alpha, alpha 2bm. Now I collect the 2bm, I obtain this term. This finally is the signal to noise expression in electrical of the optical noise, because we have not yet considered the electrical noise. So you see that the signal to noise present 4 terms. The 2 terms of short noise and a term that NO, that is not the power of the noise, but this is the power spectral level of the noise. So this is very strange. I call your attention about this term. So this NO is Pn divided by O. Okay, so it looks like an energy. Okay, because P is a power. Okay. So this is a power divided spectrum, so a spectral level. Okay, in terms of unit of measure. Okay, this NO multiply the power of the noise at 2 times the power of the signal. All this is collected and is divided by 2 bm. So what we note, again, I call your attention that the signal to noise ratio in electrical of the optical noise component, because these are optical noise components, are inverse proportional to the electrical bandwidth. So if you increase the electrical bandwidth, this noise decreases without any possibility. Okay? And also we noted that, as expected, that if you increase the power of the signal, this signal to noise ratio increases. Okay? So this is a typical behavior of the optical communication signal to noise ratio that always present. So this is why it's a problem. Because since in optical communication BM is very large, much more larger than any electrical communication, okay? Because in electrical communication this should be 1G, 2G. In optical this should be 20G, 30G, 50G, so it's very, very large. This is decreased as much as this is large, okay? Then move again. Okay, it is already said. And then move again. If the photodetector occur by means an APD, okay, we see that the average gain multiplies the numerator while the average square multiplies the noise component, because if you return to this expression, okay, we see that we have this function here. And then G squared divide G average squared, G average G squared divide G squared, we already seen that they look like 1 plus variance divided G. And this is larger than 1, because the figure of merit, of the photodiode is even larger than 1, okay, because a photodiode amplification presents an necessary variance, no, because the multiplication is not a deterministic process, but presents some casualty, okay. So if you introduce this term of a multiplication in the numerator and in the denominator, okay, we obtain this expression. That is, I have to multiply the numerator by G average, but I have to multiply the denominator by G squared average in this term of the shot noise, while here is a G average, okay? Because we already see from the shot noise process that this is multiplied in this term. Okay, so this is more complete impression of the photodiode. And then what happened? Are only the optical term. If you consider the electrical noise, you have to add the dark current noise and the Johnson noise, or the neck, in this term. We already see the expression for the Johnson noise is 2kT divided RL 2bm, okay? And the expression of the dark noise is EDC 2bm, the dark current variant. So if we add this, we finally obtain this expression. Okay, this is finally the signal to noise ratio in electrical, in our optical communication. And this is an expression valid for any optical communication system, where you see that we have the Johnson noise, the dark current noise, and the 4 optical terms. Okay? So we take a long journey to arrive here, but finally we arrive. Okay, take a couple of weeks because we have to introduce all these noise terms. Okay. Okay, this is very simple to learn because in the numerator I have alpha PS, that is count rate times again if APD exists, squared. And in the denominator I have a variance, okay, and I underline that this is a variance. This is alpha PS, no? This alpha PS in the numerator, okay, it looks like a second minus 1, okay. This alpha PS is second minus 1, squared is second minus 2. Here is second minus 2, why? Because the 2bm is second minus 1, that multiply alpha PS, that's second minus 2. So, in the numerator and denominator we have second minus 2. Okay, so there are the same unit of measure in the numerator and denominator. So, F and R is without a unit of measure, as predicted, okay? So alpha PS is 1. So don't care about E squared, and all for G you may is a number G. G is a multiplication factor, okay? So here I summarize again. Here we have the noise, the optical noise, and this electrical noise. How, if we consider a spectrum of this signal to noise ratio, no? How look at the spectrum? The spectrum looks like this, that you have to learn, okay, to memorize. That is, we have the yellow line that represents the trace of the optical filter, okay? Because optical filter is much more larger than electrical filter. Then you have electrical filter with a notch. Okay, and inside the electrical filter, you're supposed to have electrical filter 30G, you have 25G, the spectrum of the signal, in order to avoid to remove information content. Okay, and this is the gray part. So the gray part is the spectrum of the signal that contain also the DC term, of course, but we remove this. And then we have a free term of, we have the noise, because we know that the electrical noise, NOC and EIDC, is flat because it's a short noise process. Then we have this noise that is still flat because it's the corpuscular component of the Laguerre statistic, okay, PS plus PN, or the trace of the quantum noise, or the short noise term, as you prefer. So there are three interpretations of this flat term, okay? And then we have this strange fact here, that is the beating between the energy of the optical noise, because NO is a denser spectral density, that is power divide band, okay? So it means that is energy, time Pn plus 2ps. This, I remind you that we obtain this expression when we consider the mixed line, and we consider the variance of the mixed line, that is this term 2, okay? And this is still a flat term, okay, in first approximation, inside the optical band. So we have a free flat term. I underline that all these free terms cross the signal spectrum. So you cannot remove this term, because they are enter in both the optical spectrum and in the optical filter and the electrical filter. So you cannot filter away this term, okay? You have to hold this to maintain this term, okay? Everybody, you have a question about the spectrum? It's exactly the short noise process spectrum. Exactly the same picture, okay? But in this case we have three terms that contribute to the short noise. The electrical term and the optical term, okay? So the signal power ha una bandwidth 2bs e presenta a removal of the DC term. The short noise produced both by the signal and the noise present a flat bandwidth. The noise power, metal density, N0, okay, induce a variance by beating with the noise itself, in this case, and with the signal, with the term 2. The variant of the excess noise present a flat spectrum in the bandwidth 2bm. Okay, so this is the description of the spectrum. Okay. Okay, so this in yellow is the more the wall signal, is the wall signal to noise in electric. Okay, now we move from this expression to study three different situations. Okay, why three different situations? Because now finally we have to evaluate the signal. We consider three different situations, but this is a more general expression of the signal to noise ratio in the optical communication. Now we have three different situations. We just arrive on my photodetector, okay, and it is called direct detection. And we use exactly this expression. Then we arrive in my photodetector after one or more amplification. And I call this direct detection in presence of amplifier, optical. There are optical amplifier. And then the third situation is this one. We arrive maybe through an amplification to the photodetector, but before to entering the photodetector, we mix the arriving signal, okay, with another light, that is coming from here. This mixing gives a coherent detection. In all these three cases, 1, 2, and 3, we always consider this expression, okay? So we never move from this expression, okay? But simply we study how the block in this expression, that is the different term, move, okay? You understand? So we have three cases. Direct detection, that is a more trivial detection, that is photodiode behind the light. Direct detection in presence of amplifier. Why this is important? Because amplifier add thermal light in the system, okay? And direct detection with thermal, with amplifier, but in presence of a local oscillator. This is called local oscillator. That's a mix. We see in detail this. This last detection is called coherent detection, but what I emphasize here is all the three cases, this expression is so universal, so valid, that you don't move from this expression, okay? Never. Okay, so this is universal expression that is valid for whatever be the detection, okay? We simply move the importance of the different term, okay? You follow me? Now, in order to summarize, we arrive to this expression by considering the Johnson noise, the dark area noise, all this noise, and the short noise. All these three noises are a residual of the black body theory, okay? Of the Planck black body theory, okay? Because it's the KT and the H half. Then we consider the photo detection statistic, and we discover that they produce this corpuscular term and this beating noise, that's the wave term here. And then finally we summarize all this by introducing the filter BM and the filter BO here, okay? And so we built the signal to noise. Maybe that I forgot some term. There are some term, maybe there are terms closer to the DC, but since we consider a notch filter, all the term 1 over F, all the typical noise term in electric is removed, okay? So we don't consider this, because we use a notch filter, we remove all the DC term. So this is exactly the main term in the signal to noise ratio, okay? 90%, 98% are the important terms, okay? Then there are other smaller irrelevant terms, okay? But it's okay. And so now we face this free system here. So I repeat it: direct detection in presence of optical amplifier, and the coherent detection. Okay. So we break a moment here.
从来都来那个 Lambrand 来的地方有一个卖饼的。
你怎么每次都跟我介绍吃饼啊？
早饭的话没时间做的话，吃个饼我感觉还可以啊。0.7欧左右一个吧。怎么了？
在地铁站里吗？
不是啊，就在那个路上。我得准备点吃的，不然能量不够。这什么味道？啊？谁买的薄荷味的糖？
别让他给我。
colato, lì la vita è ma qui